Okay, welcome everyone. Today we have a neighbor, Meir Shimon, who's a research scientist at Tel Aviv University after doing his PhD there and a postdoc at UC San Diego. And he will tell us about Weyl-Invariant gravity and the nature of dark matter. Go ahead.
Thank you, Ofek. Thank you, everybody, for coming. I should say at the beginning, right at the beginning, that I'm not a dark matter denier. So as I'll show in a few slides, I think that there is ample evidence in favor of dark matter. My only question is what this dark matter is, right? So is it some fundamental, exotic fundamental particles? Is it primordial black holes? Or maybe the missing energy in the form of dark matter is actually stored or contained in gradients of G, of Newton's constant, universal constant G. So my hypothesis is that it's not a constant, rather it varies at the level of 1 part in, let's say, 10,000 or 1 part in 100,000 on galactic scales. And frankly, we don't have any, right? We don't have any measurement on these scales of G, right? So the idea is that just because we assume that G is constant, this is why we see that Newtonian gravity or equivalently GR in the weak field limit fails on galactic and supergalactic scales. So my assumptions, my working assumptions will be that gravitation is actually described by not by GR, but rather by a Weyl-invariant version of GR. So the idea of GR is that that at least gravitation is independent of the state of the observer, right? So this is why we can choose our coordinate system. So the law should be independent of the state of the observer. Of course, the quantities that we measure should, of course, depend on the state of the observer, but the law itself, the equation should be independent. So a Weyl-invariance tells us that not only the equation is invariant, the law is invariant to our coordinate system, but also the measure sticks, the yardsticks that we use should be at least a priori should be arbitrary. And the way that we actually infer them from the observations is just by measurement. So we use observation to also gauge our ruler, right? So what we use in standard particle physics and also in GR, we use a linear ruler. We say that the Planck scale is a constant, but maybe it's not a constant.
So can I ask, I'm
Sure.
trying to understand what you mean. So you say basically the G, right, it is not constant,
Right.
but vary with what? Vary with time, vary with space?
With space-time.
Both space and time. So it also changes with time, and it also changes as a function of location.
Yes, of course.
Now,
but for galactic physics, you don't need it to change with time, except in case of bullet cluster or something like that on supergalactic scales. But in a static configuration, it should depend only on space, not on time.
Right, but how does that coincide with the measure of cosmology? The cosmological probes of the Big Bang.
Yeah. So, for example, we have BBN. I guess that you are referring to BBN. BBN tells you that G is a constant in time over Hubble time scales over the entire age of the universe to a percent level, more or less, something like that. But if you think about G as a field, it can change in space and time. So the fact that you have 1% precision in time variation over Hubble scales doesn't tell you necessarily that it doesn't change at the level of 1 part in 10,000 on galactic scales, not in time, but in space. So it's a field.
But in that case, you would lose the sense of isotropy of the CMB.
Not necessarily. I'll refer to that towards the end. G varies at the level of 10 to the minus 5 at the last scattering surface, which basically tells you that on scales which are about 100 megaparsec, it varies very, very mildly at the level of 10 to the minus 5. And this explains the dark matter perturbations at the last scattering surface. And so it doesn't really break isotropy, because isotropy is in any case not perfect. We do measure these departures from anisotropy, but again, I'm limiting this discussion only to galactic and supergalactic scales, meaning galaxy clusters. In a future paper, I'm going to address the issue of dark matter on Hubble scales, and as I said, that at least at the level of perturbations, this can easily be explained by this mechanism. I will be assuming that the standard model of particle physics is as is, so I'm not going to conformalize it. I'm not going to extend it with a Weyl symmetry, although people did consider this possibility. Again, I don't need to do that in order to explain dark matter, so I'm not going to do that. I'm just introducing the minimal, changes, modifications that I can, that I have to in order to explain this dark matter phenomena. I will also make a distinction between active and passive gravitational masses. Now, this idea goes back at least to Bondi, Hermann Bondi, 1957. But I suspect that people consider this possibility even earlier. Now, what is active and what is passive gravitational mass? We are talking about, about Newton law of gravity, even at that level. So you have the source, which is the active gravitational mass, and you have the test particle, let's say, the passive mass, the mass of the object that feels this attraction. Of course, it doesn't really have to be a test particle. You can think about even a binary system, that each object in this binary system has its own passive and active mass. I should say that the equivalence principle does not break down because of this distinction that I'm making, because the equivalence principle only requires that the ratio between the passive and inertial mass of an object should be a universal constant. It doesn't tell us anything about the active gravitational mass. So I will assume that this universal constant is unity with no loss of generality. We do the same thing in GR, but in distinction from GR, the active gravitational mass will be free to vary in space and time. I'm talking about, like, of course, it's a meaningless statement to say that the active gravitational mass varies in space and time. I mean that if you think about an individual particle, fundamental particle, so this particle has its passive mass, but also it has its active mass, and they are not necessarily the same, in the sense that I'll show in a few slides. So the idea is that both G, big G, Newton's G, and the active gravitational mass weakly vary over galactic and supergalactic scales, as I said earlier. And so dark matter phenomena could be accounted for by these small perturbations, these small variation, again, at the level of 1 part in 10,000 or 100,000. And so the missing energy is actually contained in these gradients of G and M. Now, G and M are regulated, governed by some scalar field. I'll show that in a few slides. So I wanted to spend a few minutes about the dark matter problem. What kind of evidence do we have in favor of dark matter? And as I said at the beginning, I do believe that there is dark matter. The only question that I have is what this dark matter is. So this is Vera Rubin. She found about 30 years ago that if you plot the velocity curves as a function, the velocity as a function of the distance from the center of galaxy, what you expect based on the observations of the luminous matter is this dash curve A. This is just from Newtonian gravity, but what we actually observe is the flattening of the rotation curve. This is curve B. The simplest interpretation of that is that you have a non-luminous matter, dark matter, that supports these large velocities far away from the center of the galaxy. So this is on galactic scales. Now, Fritz Zwicky, 45 years earlier, from his observations of velocity dispersions of galaxies within a cluster, and assuming that this cluster is a virialized system, he realized that there is not enough matter. Again, assuming that the only type of matter is luminous matter, to explain these large velocity dispersions. And again, he concluded that there must be some dark matter on galaxy cluster scales. And this is a more modern evidence on these scales for the existence of dark matter. So you can see here the image of the background, which is lensed by a galaxy cluster. You can see here all these small arclets. And in order to explain this level of distortion in the image, you need, again, much more mass than we actually observe. So this is another piece of evidence in favor of dark matter. Now, if we go to even larger scales, and we observe a CMB, which is a snapshot of the universe when photons just decoupled from CMB photons just decoupled from the grip of the baryons, when the universe cooled down enough due to expansion for that to happen. This happened at redshift at around 1100. So here we see a map of the sky projected on the plane. This is why it's distorted. It's not circular, obviously. It's just a projection. You can see here the small perturbations, small fluctuations. We are talking here about a level of 10 to the minus 5. So we are talking about a fractional level of 10 to the minus 5. Even at the 70s, upper limits, mid-70s, upper limits on these perturbations were at the level of 10 to the minus 4 or so. And people realized even back then that there is a problem with a standard cosmological model back then, right? Without dark matter. So dark matter was introduced to cosmology shortly after it was proposed as an explanation for galactic scale phenomena. So it was about 80, 81. So even at the mid-70s, people realized that there is a problem. Why? Because in this expanding universe, the overdensity of matter grows linearly with redshift. And this is a general result from just perturbation theory on an expanding background, assuming all the standard assumptions of cosmology. And this is a problem. Why is it a problem? Because if the entire matter in the universe is in the form of baryons and of course some small fraction in the form of neutrinos and so on, but only standard model particles, then this perturbation, this level of 10 to the minus 5 in radiation should also be the level of perturbations in baryon density because they are tightly coupled until this moment. And if you just multiply 10 to the minus 5, or back then people were thinking about 10 to the minus 4 by 1000, which is the redshift of recombination, you get 10 to the minus 2 or 10 to the minus 1, still deep in the linear regime, or at least in the linear regime. And of course, this is an absurd result because we owe our existence to nonlinear structure, and we infer from observations that the perturbation should be only linear. And so in order to go around this problem, people invoke dark matter. So dark matter is free from the coupling with radiation. It could start clumping much before recombination. Basically, radiation matter equality at redshift of 3,500, more or less, 3,400. And so by the time that the baryons are released from the grip of the photons, they could fall into these pre-existing gravitational wells. And by the present, we can end up with nonlinear structure. And so this is another evidence in favor of dark matter. Another piece of evidence that I'm not going to talk about, which I'm not, again, I don't have yet, let's say I didn't publish my solution about it, is the dark matter at the background level. Of course, there is you know, from just measuring the background of the universe, we see that we need about 5% baryon. We also know that number from BBN, Big Bang nucleosynthesis, the formation of the light elements. We know that we also need 25% in the form of dark matter, cold dark matter, non-relativistic matter, basically. And the remaining 70% is in the form of dark energy. So this is another evidence in favor of dark matter. And the last one that I'm going to discuss here today is the bullet cluster. So a bullet cluster system is a system of two colliding clusters. Here we see the aftermath of the collision. So the bullet one goes from left to right, the other one goes from right to left. And so if you combine just lensing data and X-ray observations, so the lensing, these are just you know, synthetic color code. So you see the center of gravity, this is the blue, and in red we see the luminous matter, the matter that we can observe with X-ray observations. And we see that it's lagging behind the blue lobes. And the simplest interpretation is that the dark matter, which are the blue one, that is the majority of matter in this system, go through each other with basically no interaction. And the baryons, of course, interact with each other, therefore they are lagging behind. And so this is another explanation or another reason to believe that there is some form of dark matter. Now this cold dark matter CDM paradigm does not come without its own challenges. One of the challenges is the cusp core problem. The idea is that in this kind of let's say the simplest scenarios or explanation for cold dark matter is some kind of matter that doesn't interact with, you know, with light, doesn't interact with radiation, doesn't have any very weak interaction with all other forms of matter. So basically, in order to simulate it, you need only to couple the Poisson equation. We are talking about weak gravity, right? So Poisson equation, Euler, and continuity equation, basically a statement about the energy momentum conservation. And when we do that on galaxy cluster scale, for example, we get the profile. And so the profile turns out to be very cuspy. You know, when we compare that to observations, we see that the inferred profile of dark matter is not so cuspy as predicted by simulations. There is also the problem of missing satellites. When you do a similar simulation on galactic scales, you expect some satellite galaxies. And what we actually observe is a smaller number of satellite galaxies. Of course, people say that these measurements are subject to selection effects. You know, it's still debatable in the literature. I'm not an expert on that, so I cannot tell you my take on that. But I understand that this is one of the, let's say, problems of CDM. And the last point is that in spite of 3 or 4 decades of search, we didn't find any, right? So all the other options are on the table. Maybe it's not made of particle, right? So this is the idea. And here is a Venn diagram due to Tim Tate from UC Irvine. So you can see here, you know, a zoo of families and scenario for dark matter and all the overlaps between them. And for example, the MSSM, the minimally supersymmetric model, has about 120 model parameters. And under certain simplifying assumptions, you can reduce the number to only 20. And each model here has its own parameters. And in principle, you can, of course, falsify these models, but I doubt it that you can, you know, entirely falsify the paradigm, the CDM paradigm. It's very similar, by the way, to inflation. We also have, you know, one of the key building blocks of our cosmology is inflation. Again, you have a zoo of models. In principle, you can falsify, but my question is, practically, can we falsify this model? It's not so clear to me. For example, this scenario, warm dark matter, was basically falsified already. Again, but you know, there are many others that are not falsified, and people are still, you know, insisting of considering like a mixture of warm dark matter with cold dark matter in many kind of models. So it is falsified as a major contribution to dark matter. Maybe it's a small fraction is still in the form of warm dark matter. So it's an endless, you know, industry of possibilities that people consider. Did someone want to ask a question? Because I see that one of the microphones is still open, because I hear some.
There's something dark photon written at the left side. What is that?
Okay, so people, you know, dark photons, it means that it's basically a massless particle, but it doesn't interact with the electromagnetic charge. And again, I'm not an expert on these models. I know very little about them. I just wanted to show, you know, just to give us an impression of what kind of models and scenarios people are talking about, because, you know, we have to understand that this, you know, this particle dark matter, exotic particle dark matter is a scenario that it's a scenario, right? It's not a one single model, and it's very hard, at least in my mind, to really falsify it, because people, you know, come up with, we are very creative, right? We can come up with many models, and I'm just saying that it's hard to, in practice, to falsify them. So now I wanted to say a few words about dark matter. So how do we infer the existence of dark matter? So we have both kinematic and dynamical ways to infer the gravitational potential, the Laplacian basically of the gravitational potential. So one of them is just from the geodesic equation. This is just a kinematic probe of the gravitational potential. Basically tells us that the gradient of the potential equals minus the acceleration. So this is just a statement of Newton's second law. If we consider, for example, the geodesic of an incoming photon that is being deflected by the transversal gradient of the gravitational potential, we get this lensing map. So this is just a map of the deflection angle, a two-dimensional map of the sky. So basically, it's just the impact that the photon suffers while going through a lens or next to a lens. It's just a transversal gradient integrated along the line of sight. So the left side is an observed quantity, the right-hand side is theoretical. Basically, if we take the divergence of the two sides, we get here basically an estimate of the integrated Laplacian of the gravitational potential integrated along the line of sight. And so from this divergence of the map, or the lensing map, we can infer, under certain assumptions, we can infer the Laplacian of the gravitational potential. If we go to dynamics, then it's even simpler, right? We just have a Poisson equation. We are in the weak gravity limit. So from just having a measurement of the baryon density, from, let's say, from X-ray observations, we can deduce the Laplacian of the gravitational potential, but this will be the gravitational potential that is sourced by baryons. Now, if we compare these two Laplacians, the one that I showed in the previous slide and this one, we see that there is a mismatch. In order to correct for this mismatch, we introduce this Laplacian of phi dark matter, let's call it the potential which is sourced by dark matter, to both sides. And we see that the energy density of dark matter is basically the Laplacian of this new function in units of 4 pi g, right? So it's not necessarily made up of particles. We don't have any direct measurement of the energy density profile of dark matter. We infer it from solving the Poisson equation if we have a measurement of the dark matter potential. So I mentioned at the beginning 3 types of masses. Let me just say a few words about that. So this is a Newton's law of gravity. This is gravitational constant, of course, active gravitational mass and passive gravitational mass, the source and the mass of the source and the mass of the particle that fills this gravitational attraction. We also have an inertial mass that appears in Newton's second law. And if we compare between them, we see that the acceleration experienced by some particle will be independent of its properties. And this is the equivalence principle if the ratio between the passive mass and the inertial mass is a constant. Again, I'll be assuming that this constant is 1, the same way that it is assumed in GR. Now, a few words about Weyl transformation. Weyl introduces symmetry for his theory. He proposed his theory a year after Einstein finished his formulation of GR. And the idea is the following. You rescale, you have a freedom to rescale your fields according to their dimensions, physical dimensions. For example, the metric field, the field that determines the geometry of space-time, has units of length squared. Therefore, it scales like omega squared times the metric. Omega is an arbitrary function. This is a symmetry. You can think about that as a gauge symmetry of the theory. If we consider the Lagrangian density of matter, the source of gravity, it has units of 1 over 4-dimensional volume. This is why it is rescaled this way, like omega to the minus 4. Again, omega is a function of a general function, arbitrary function of space-time. And here you should see that it scales like omega to the minus 4. In case of a scalar field, for example, a scalar field has units of mass in 4 space-time dimensions, which means that it has units of 1 over length, inverse length units. This is why it scales like omega to the minus 1. Now, if we consider a Weyl-invariant version or extension of GR, then we can use this symmetry to generate infinitely many solutions out of any given solution. For example, you find the Schwarzschild solution, you can rescale all the fields to find new solutions. Basically, in the case of Schwarzschild solution, this is just a vacuum solution. So you have only the metric field, and the metric field scales like this. Now, there is no problem with this because null geodesics are invariant to conformal rescaling, to this kind of scaling of the metric. But again, this theory in its most generality does not really rescale only the metric, but all the fields according to their physical dimensions. Of course, this omega can be 1 at, for example, on solar system scales, and can be 1.00001 on galactic scales, right? So it can vary on, on scales because it's a function of space and time. So a few words about Einstein theory of gravity and how we actually elevate it or promote it to be a Weyl-invariant version of this theory. Ken, yes, someone wanted to ask a question?
I want to ask you again. Go back to the previous slide. So you say that omega, right, the scaling factor of the theory, or the is a function of x, right? And x, you say, is space and time.
Right.
but then I refer you again to the cosmic microwave background fluctuations.
Yeah.
Like if what you say is correct, then from the structure of the baryonic acoustic oscillations, you should be able to see these effects, because that will affect the locations of the dips on the different scales. And then this is something which you should be able to probe it there in principle. Maybe it's too small to be below the detection limit. But if you're putting different scale dependent factor, so a scale factor which depends on the size, this is something which you should be see the imprint of that.
Yes, of course. I'm not saying otherwise. I'm just saying this is the same way. I mean, you can think about that. I mean, the way to think about it, I mean, the way that I think about that is the following. In principle, you could think about making a simulation of the entire universe, right? Producing a simulation of the entire universe. I mean, just as a Gedanken, just a thought experiment. And you can determine the value of G, of the metric, G mu nu, at any point in space and time. You can do the same thing for the scalar field phi, or G, basically, as I'll show in in the next slide, basically. And it tells you something about omega, because phi goes from a constant in GR to this.
That's what I'm saying. I'm saying that if you play this game, you should see the imprint of that scale factor omega on the structure of the CMB fluctuations.
Of course.
So
I'm saying that CMB fluctuations, of course, we do need dark matter in order to explain the CMB perturbations, not only baryon perturbation, but also dark matter perturbation. These are at the level of 10 to the minus 5, more or less. And omega should be varying from unity at this level at the time of last scattering on the relevant scales, which are the horizon scales at redshift of 1100, of course. So think about omega as a function of space and time, and you have a box, 4-dimensional box, in which you register what value of omega you found in each point of space and time. Obviously, you can do a data compression the same way that we do for G mu nu, at least on the larger scales, and find that it's scale dependent, not only space-time dependent. So you can find, I would assume that you find that on typical scales at given typical time scales, omega departure from unity at that level and not in another level, at a different level. So let me go back to Einstein-Hilbert action, from which we can derive the Einstein equation. So this is just a standard gravitational model. We have here a curvature, a curvature scalar, just a scalar measuring the curvature of the universe in units of 16 pi g. Again, I'll be assuming that h bar and c, the speed of light, are set to unity. So this combination has units of 1 over 4-dimensional volume, because we multiply it by the volume element, which is 4-dimensional, and this I is just the action in units of h bar. It's dimensionless. So we do need the G here in the denominator, because R has, in order just to set the units right? And so the energy density of matter has units of mass over volume, or mass over 3-dimensional volume, or equivalently inverse 4-dimensional volume. So everything works right, and you can define the Planck mass square to be 1 over 8 pi g, and you get this expression. Now, if you want to promote the Planck mass to be a scalar field, just varying in space and time, so you get this expression. So this action was proposed by Stanley Deser 50 years ago, with two differences from the one that you see here. First of all, he didn't consider the explicit dependence of the matter Lagrangian on this scalar field. And another difference is that he took the scalar field to be a real field, and here I'm considering to be, not here, but in the paradigm that I'm I'm using a complex scalar field. Actually, we don't need the phase of this scalar field for the purpose of galactic physics. I need it for my model of the very early universe. I have a bouncing model for this purpose. I do need the phase, but this is a different story. Anyway, if the mass is varying with space and time, in order for it to be dynamical, in principle, you have to add a kinetic term. So here we have just the gradient of the scalar field squared, right? And here we have an explicit dependence of the meta-Lagrangian on this scalar field and other fields, which are collectively denoted by psi. This include the Dirac field, the electromagnetic vector field, and so on and so forth. If we set phi to be a constant, this particular constant, then this kinetic term drops because phi is a constant, and you recover Einstein-Hilbert action, right? So my proposal is that phi might be actually space-time dependent. So let me just digress and say a few words about Weyl original theory, because it might have some connection to a theory that I'm describing here. I mean, in addition to the fact of it being Weyl-invariant. So his theory was curvature squared. I'm not going into the details, but the idea is that unlike in here that you need to set the units and by introducing G, his theory here, you have something like curvature squared, not a scalar curvature, but Weyl tensor field squared. But anyway, you don't need G because of the units. So you may wonder about the Poisson equation, about the weak field limit. People thought about that for many, many years. Of course, very early on, people realized that the Poisson equation is replaced by a fourth order field equation, again, because you don't have G. And of course, you have a much richer set of solutions, again, without G. About 30 years ago, Mannheim and Kazanas found an exact spherically symmetric static solution of this theory. And so this solution was a metric solution, looked like a Schwarzschild de Sitter solution with a linear potential correction. And this linear potential correction was able, this is what they contend to explain the rotation curves in galaxies. So this was a very exciting indication that this kind of relativistic theory might, unlike Mond, by the way, might explain dark matter phenomena. Of course, very early after their discovery, people realized that in order to simultaneously explain both rotation curves and lensing by, for example, by galaxy clusters, this linear term has to flip its sign, and this posed a challenge to the theory. People, again, I don't want to get into details, but people thought that they found a way around this problem. I'm not convinced that this is a solution. So I was looking, by the way, I found the same solution in my theory. If I impose a static spherical symmetry condition on the solution, but again, I'm not convinced that this is a solution to the problem, to the dark matter problem. It's at least not a compelling one. Yes.
Can I go back one slide? I did not fully understand what you mean by a spherically symmetric static configuration.
I'm talking about a vacuum solution of the field equation. So you have no matter, something like a Schwarzschild. But they found that unlike a Schwarzschild solution, which is a non-vacuum solution, they found something which is a generalization of the Schwarzschild solution, which has, the potential looks like a -2 beta over R plus gamma R plus some constant times R squared. And this is because the equation is not second order, it's a Laplacian of the Laplacian, so it's fourth order. So you have two more integration constants. And again, you get that in a vacuum solution, you have no matter right? Like in Schwarzschild solution.
So that's supposed to represent the solution of stars and galaxies? Like the curve.
Yes, you know, I'll skip a few slides ahead to one of my backup slides and show you the, so they are talking about this kind of metric. And again,
no, I'm not asking about it. I'm asking about, so what physically that's supposed to represent?
Yes, of course.
Of a galaxy?
Since it's a vacuum solution, this means that outside of the core of the galaxy, outside of the baryonic matter, you basically have a vacuum. So this solution applies and you get this linear term that can explain rotation curves.
How is that different than the Brunson-Dicke theory?
So yes, I have also a backup slide about that. If time will allow, I can say about that a few words, but if this is not an urgent question, let's go back to this question at the end. So to find the field equations, and again, the details are not really important, but I wanted to at least schematically show how it looks like. If we make a variation of the Weyl-Invariant scalar tensor theory that I showed you, with respect to the metric field, you get this equation. So this equation basically is similar, just a generalization of Einstein equation. Here, instead of 1 over 16 pi g, you get 1 over 8 pi g, excuse me, you get this thing, which again, phi is a very weakly varying function of space-time. But here, this is an important thing. You get a correction to the energy momentum tensor. So basically, this is a, baryons, neutrinos, radiation, whatever. And here we get a correction. Now, this correction is built up by just gradients of the scalar field that I showed earlier. The same scalar field that determines the Planck mass, basically a Newton's constant G. So here we have second order derivative, here we have first order derivative squared, here again we have second order, and we have first order derivative squared. And basically the new contribution to the energy momentum tensor comes from gradients. They can be temporal or spatial gradients of this scalar field, basically of Newton's constant. If we similarly vary the action with respect to the scalar field and find the extremum of this variation, we find this scalar field equation. Now, if we take the trace of this one and combine it with this one, again, I'm not going into details, I just want to show the idea, you get this equation. So this is a constraint equation. You see that you have here no derivatives of phi that determines the trace of the energy momentum tensor. The trace of the energy momentum tensor is proportional to the energy density times 1 minus 3W, where W is the pressure in units of energy density. Now you can see that if the matter Lagrangian, as Deser put it, is independent of phi, you get that the field equations of the theory that I showed you, scalar tensor theory, the Weyl-Invariant scalar tensor theory that I showed you, are only consistent if the energy momentum, trace of the energy momentum tensor is vanishing. So this means that W must equal 1/3, which corresponds to radiation. In the case of non-relativistic matter, dust, which is a source of gravity on galactic scales, W equals 0, and the energy momentum, the trace of the energy momentum tensor is non-vanishing. This tells us that the matter Lagrangian should explicitly depend on phi. Now, for those who asked about Brunson-Dicke theory, in Brunson-Dicke theory, in general, you have here another term, which is a phi box phi, something like that, which tells you that it's not a constraint equation, but rather it's a dynamical equation that tells you how phi should vary in space and time. And this, of course, would ruin the Weyl-invariance, right? The Weyl-invariance tells you that phi, because it's just phi 0, the constant that we see in GR over omega, and since omega is an arbitrary function, should be independent of any dynamics, right? You can choose your ruler at will. Now, if we integrate this constraint equation, we get this relation that the energy momentum tensor scales like some power of phi of the modulus of the scalar field. In the case of radiation, it's independent of a scalar field. We saw that already. But in the case of dust, it's linear in the scalar field. Now, this does make sense, right? Because the energy density of non-relativistic matter is basically the mass over the volume. Now, if the mass is the active gravitational mass, then phi, which has units of mass, determines the active gravitational mass. This is where we see that the same phi that determines the Planck mass also governs the active gravitational mass. Now, this theory now is something that we can work with in galactic environments. We are not limited only to radiation. Now, if we consider linear perturbations of the scalar field, just plug it in this, right? Phi is just phi 0, the same phi that we see in GR, times 1 plus some epsilon small dimensionless number times a function of space, arbitrary function of space and time, we get that all the gradient square that I showed earlier terms drop from the definition of theta mu nu, which is just the correction of the energy momentum tensor, and we end up with this second order contribution. Now we can see the origin of dark matter. Remember that I showed you earlier, a few slides back, that the energy density of dark matter is the Laplacian of the dark matter potential in units of 4 pi g. Now we see where it can come from small variations of this scalar field. The same scalar field that determines Newton's G and active gravitational masses. So this is one of my last 2 slides, I think. If we start with a weakly perturbed space-time in the framework of GR, so where G is a constant, big G is a constant, it looks like that. You have here 1 minus 2 phi baryon, because we have only baryons. Let's say that we don't have dark matter and everything, times dt squared. We have here a mixing term between space and time times the peculiar velocity. On galactic scales, we are talking about small velocities with respect to the speed of light. So this is already a linear correction. And here we have the same phi. Note that here you have minus minus times the spatial part. Now, how do we add the dark matter potential? We just say that omega is 1 plus phi dark matter potential, which is a function of space and time in general. Again, I assume that this phi is small. On galactic scales, phi is at the level of 10 to the minus 4, more or less. And apply a Weyl transformation. Since omega is small, omega squared is 1 plus 2 phi, and so we get a shift in the gravitational potential, the same shift that we need in order to explain dark matter potential. Remember that I can choose omega or phi dark matter as I wish, because this is a symmetry of the theory that I assume this symmetry to be a valid symmetry of gravitation. Of course, there is a cost to it, but before that, I should say that here you see that you notice that I didn't introduce this 1 plus 2 phi dark matter factor, because this is already a first order term, so I keep only first order terms here. And the cost is that I cannot do whatever I want, right? It's a symmetry of the theory. I have to if I rescale the metric field and get the shift, the required shift in the gravitational potential, I must also rescale all the other fields. For example, I have to rescale G times the active gravitational mass, which determines basically the strength of the gravitational interaction. So G is 1 over the Planck mass squared. So we get here phi to the minus 2 times phi. And this tells us that G times active gravitational mass is shifted by this prefactor, by let's say 10 to the minus 4. This is a relative change. The same goes to G, right? So basically, there is a correlation between variations of G, if we are able to directly measure G on galactic scales, and the dark matter potential. the same dark matter potential that we need in order to explain the discrepancy between kinetic and dynamical determination of the gravitational potential that I showed earlier. Now, since phi dark matter is an arbitrary function, I can choose it at will. In particular, I can choose it to be the NFW, the Navarro-Frank-White gravitational potential, the same profile that they use. Usually, we are used to see it in terms of energy density, not in terms of gravitational potential, but in order to get to the gravitational potential, you just integrate the Poisson equation. We get this dependence, which is 1 over R. And here we have a multiplicative logarithmic correction. RS is an object-specific parameter. You fit the data and you find RS for a particular system. Of course, you can choose other forms of potential. And again, there is no physics behind that. There is only mathematics. It's not a physics of cold dark matter particles. It's not a Poisson equation coupled to the Euler equation and continuity equation. It's just a statement about the symmetry of the gravitational interaction, that it's Weyl-invariant, and you do have this freedom. This is of course, my assumption. In principle, you can find even a better fit to observations by just guessing a form of the gravitational potential, not only on galactic scales, but on galaxy cluster scales and so on. Now, let me just summarize. Dark matter phenomena on galactic and galaxy cluster scales could be explained by a Weyl-invariant version of GR. So it's not, actually, it's not, as I said, it's not a new symmetry of gravitation, but at least it's not an accepted symmetry of gravitation. So I'm proposing that maybe dark matter phenomena just have to do with small variations, very mild variations of G or G times active gravitational mass on these scales. Of course, on solar system scales, we don't see it because it's in some way, and I cannot tell you from the theory, of course, we have to go to observations, does depend on the scale. So we don't see it on solar system scales where we do have precise measurements of G, but it might account for dark matter phenomena on galaxy and galaxy cluster scales. So I'm ready to take a few questions. I know that one of you asked about Brans-Dicke. I think that I partially answered this question, but if you want a more detailed answer, I'm ready, of course, to elaborate on that. Thank you.
So I have a few questions.
Go ahead, please.
So first one, in spirit, what you do is very much resembling the idea of Mond, which you should be able to retrieve back as a non-relativistic version of that, right? But essentially in the Mond, you also add up some constant to the Poisson's equation, right?
Well, I'm not adding a constant without paying the price. Well, it's a small price, but I do have it, right? So I do have to rescale all the other fields, right? Because it's a Weyl-invariant version of GR. I cannot, change only the metric field. This must be expressed or manifested in the transformations of other fields.
That's okay, but then how would that be different than the Teves generalization of Mond?
Well, I think that in Teves you do need a tensor and also a vector, right? Fields. Here I have only one scalar field. In addition, I think that I think that to the best of my understanding and knowledge, Teves is not a Weyl-invariant theory. Here I'm proposing that there is a symmetry behind. I'm not constructing a model, I'm just imposing a symmetry on GR, a symmetry that currently GR doesn't, well, it's not accepted, at least not accepted view that it has this symmetry, right? So I think that these are basically the main differences. Again, I'm not introducing a constant like A naught or something into my theory because this is a Weyl-invariant theory. So it means that I cannot, it's forbidden to have, let's say the rule of thumb is that it's forbidden to have any dimensional constants here in the action. By the way, the prefactor here, 1/6 and not 1/4 or 1/8, exactly guarantees that the combination of these two, I failed to mention it, are Weyl-Invariant if you multiply it by the volume. If it was a different prefactor, then it wouldn't be a Weyl-Invariant. And in principle, you can consider small corrections to 1/6 and constrain them by observations. But this is a side remark. Ken, yes, but you had other questions as well.
Yeah, the other thing, I mean, I'm trying to think of, ways that there's spatial dependence of G mu nu could be constrained. So one obvious thing which I already mentioned is this, CMB, the places of the deeps in the CMB. Another one would be the stability criteria, right? Like the tumor criteria for galaxies, right?
Of course, and also for stellar evolution and so on and so forth, right?
You say that G mu nu evolves on scales of a galaxy, right? Then this should affect the evolution of galaxies, right? So you should see different types of galaxies relative to what you'd see without it. Right?
Yes, but we right. But again, I can choose this phi to be. You remember, I can choose this phi to be whatever I want. So I can choose it to be exactly this one, the same one that you see in the standard model. But you say, okay, but you can change the metric, but you also change G. Again, you are right. I change G at the level of 1 part in 10,000 or 1 part in 100,000. And the question is, how big a change is this, or how big an effect this would have on galactic evolution? I don't know. I didn't check that. I suspect that it's not going to be a big change, right? There are so many unknowns in galactic evolution, I think, that this 1 part in 10, yes, excuse me?
The tumor criteria is pretty strict.
Okay. So I cannot tell you, I mean, at least, well, depending on what, let's say, stage of the evolution you are talking about. I guess that later on, the physics is more complicated, and you can allow for some tolerance in the variation of G. I don't know, I cannot tell you what constraints do we have from galactic evolution on the precision of G. I do know that even from our solar system, we hardly know G to a precision of 1 part in 10 to the 5, right? So I wouldn't expect that on galactic scales we have a better or more precise measurement of G.
I don't know. But then I guess the last question I have is, what would you refer to the Xenon experiment for the WIMPs, right? They had this 2 sigma report a few years ago. How would you interpret these ones?
Well, I think that 2 sigma is not sufficiently high, right? It's at least not in the standards of particle physicists. We are talking about 5 sigma or so. I think that this is not This is not an accepted. It's not part of the standard model of particles physics, right? So every now and then we do hear about like 1 sigma, 2 sigma, 3 sigma. Again, I'm not playing it down. I'm just saying that we don't have, right? We didn't. I haven't heard that there is a declaration. There was a declaration about dark matter particle. I mean, we never found a dark matter particle, right? At least not beyond any doubt.
2 sigma.
What?
They found within 2 sigma, right?
2 sigma is not. I think that we are going to agree on that. That 2 sigma is not enough, right? But anyway, even if you find a dark matter particle, as I said at the beginning, it has to be, the properties of this particle have to explain all the phenomena on scales from galactic all the way from galactic to super Hubble scales. So it's not enough to find a dark matter particle. You have to see that the abundance of this particle is sufficient, and the other properties are sufficiently known in order to explain the wealth of observations, right? So I mean, I think that we are still a long way from establishing, let's say, an accepted dark matter particle candidate. Well, let's say accepted dark matter candidate for dark matter.
Right. Thank you.
Thank you. Any other questions?
Yeah.
Yes, please.
At galactic scales, if you have this difference of 1 in 10,000 part, then at megaparsecs you have 1,000 times more, right? So we have recently measured these gravitational waves, which is just the fluctuation of gravitational potential at large distances. So does it predict something else in the observations of gravitation?
Oh, you were talking about gravitational waves?
Yeah.
So you see that this is, we actually, I'm just multiplying by scalar field, and this just shifts the gravitational, the scalar part of the gravitational potential. It doesn't have any impact on the tensor part, right? So there is like, I don't show it here, but there is a tensor part and also a vector part in principle, right? So the tensor part is not affected by this shift of, let's say, a shift of the scalar potential, because again, I'm not using any tensor function, but rather a scalar function. So I don't think that it's relevant to any gravitational wave physics. Yes, please.
Well, if your scalar field is not conserved, you can have modes of that propagate in space as well, and you have your scalar gravitational waves.
Okay, so you are talking about propagation of phi, but you remember my constraint equation. Let me show it again. This is my scalar field equation. Basically, I traded this equation by this equation by just combining the trace of the generalized Einstein equation with this equation. So if we go to a scalar gravitational wave that you mentioned, so here, this is a Brans-Dicke theory, and this is a famous Brans-Dicke equation. Now you see that phi is phi of Brans-Dicke has units of mass squared. So it's basically up to some prefactor of order unity. This is just my field squared. This is a phi of Brans-Dicke. So you can see that if the matter is not traceless, you have phi is actually a dynamical field because it's governed by some wave equation, right? So this is just the Lambertian. Unless omega of Brans-Dicke is -3/2. And this is exactly my theory. I didn't say that, but my theory is Brans-Dicke at -3/2, but I also have an explicit phi dependence of the energy momentum tensor or matter Lagrangian, and there are other terms. So you can see that if Brans-Dicke parameter is -3/2, then you lose all this part that governs that gives you the wave nature of phi that you were talking about. And then you end up with this equation. So I don't have scalar gravitational waves in my theory. Again, just because the prefactor here is 1/6, and because it's basically Weyl-Invariant, just because of that. Otherwise, I would have these scalar gravitational waves that you are talking about. Yes.
Does that form a constraint on the Lagrangian parts dependence on phi?
The Weyl-Invariance?
Yeah, because it looks like the middle term you have.
This one.
Yeah, that looks like it will create standard waves. The first term is like a mass term that you zeroed out.
Right.
So the Lagrangian part could still contribute sources.
This one? The metal Lagrangian?
Yeah.
Yes, it does. And this is what you get. You get these two equations, this one and this one. And if you combine this one with the trace of this one, you get this one. So I can just for transparency, I just ignore this one and I look at this one. You see that phi is not determined by the energy momentum tensor. Again, if in terms of Brans-Dicke, if omega is not -3 which in my case is, in my parameters, field parameterization is 1/6, then you will get here a term which is proportional to, on the left-hand side, phi times box phi. And then you will, again, end up, as you mentioned correctly, with scalar gravitational waves. But otherwise, phi is not determined by the equations. And again, why it's not determined by the equations, let me just show, again, go back here. If you go from the Einstein frame, from GR to arbitrary frame, then phi, you start from phi naught, which is just a constant, this constant that I showed here. You start from phi naught and divide it by omega, but omega is an arbitrary function. So the phi here on the left-hand side is arbitrary function. So it cannot be determined dynamically. It has to be determined observationally. Now you can say, oh, what is so, I mean, is it a physical theory at all? So I can refer you to GR. In GR, you also have a freedom to choose your coordinate system. And how are you going to determine your coordinate system? By just making an observation. You find the highest symmetry in which you can describe your observations, whether it's a spherical symmetry, elliptical symmetry, or whatever symmetry, right? So this is a whole idea of freedom. And so Weyl transformation just tells you that phi can be arbitrary. It cannot be determined by the field equations.
So in GR, you typically try to measure things that are gauge invariant or coordinate invariant. You find those things which are not dependent on your coordinate system. The question is, if you define phi as completely free, then would omega be observable? Would some combination be observable? What would be the observables here?
To the extent that G is observable, then omega will be observable. But if you are searching for scalar quantities, but not only under coordinate transformations, but rather under Weyl transformations, then you can think about dimensionless combinations of scalar fields. For example, phi squared times phi to the fourth power times the matter Lagrangian density is a dimensionless quantity, and it's also a scalar quantity under coordinate transformation. So this quantity will be invariant to both, under both coordinate transformations and Weyl transformations. So you are pointing towards an important point here, is that scalar fields, as we know them in GR, are not scalar fields under Weyl transformation. For example, the curvature itself, the Ricci scalar, is not, just because it's dimensional, it's not Weyl-invariant. It's not a scalar field. And let me show you just this one. Here, you see, let's say that you don't have a curvature at all. You just have this canonical kinetic term of the scalar field and the matter Lagrangian. Now the matter Lagrangian, let's say that it has the right scaling with the fields, and this combination of the matter Lagrangian density times four-dimensional volume element is scale invariant. But what about this one? This one contains derivatives of omega. You can see here, right? If you go to the new frame, then you have derivatives of omega, and obviously this times this one cannot be Weyl invariant. So you are forced to introduce a curvature term, because the curvature term depends on the metric field and its derivative, first and second derivatives, and a combination, this particular combination between this term and this term will kill all these gradients of, or derivatives of omega, and you get something which is has a scaling of omega to the -4 to cancel the omega to the power of 4 from this volume, four-dimensional volume element. Now, if you do an integration by parts of this kinetic term, you get minus phi times box of phi, and it has units of course of phi to the fourth order. Then if you divide this combination by phi to the fourth order, then you get a scalar field to both, under both coordinate and Weyl transformations. So the very fact that R alone is not a scalar field under Weyl transformation just tells you that, for example, that singularities that we are familiar with in GR are not really singularities, if you accept that Weyl transformation is a symmetry of gravitation. So think about that, that you do see that the universe is very curved towards the, let's say, initial singularity of the Big Bang. But this is just because you are using a measure stick which is linear in the, in the units that you measure. But if you have an adapting unit of measure, let's say the Planck length is shrinking, then you don't have any singularity. Of course, there is a cost to it because phi, the scalar field, let's say the masses, the active gravitational masses in this cosmological model will have their own evolution, and then you get, you get the singularity from the back door in the scalar fields, not in the metric field. So I'm not saying that this is a way to evade singularities. I'm just saying that what we think is a scalar field only under coordinate transformation, but not necessarily under Weyl transformations. So this was a long answer to your question, sorry. But I hope that this answers your question.
Okay, any other questions?
I have one more. If dark matter is a conventional matter, then can it self-gravitate? If it does, then can you expect dark stars or something?
Again, you said that if it's a, what kind of matter?
Like people say it's made of some kind of particle or something. So if it is a matter.
If it turns out to be like some conventional matter, but for some reason that we fail to observe it or to see it in the electromagnetic spectrum, what would they say about the theory? I would say that omega is 1. And then the theory reduces to GR, and GR is the right theory of nature. The whole idea is that if dark matter is never found, maybe it's because G varies very, very little very mildly on galactic scales. If you find the right dark matter particle that explains all the phenomena, if you find the explanation for conventional matter that for some reason that we don't observe, then I would say that omega is set to unity on the entire universe on all scales, and you are back to GR.
Yeah.
Any more questions? Okay, if not, let's thank Meir again.
Thank you. And thank you for your questions.
You're welcome, and thank you. And I'll see you for the seminar next week. Bye-bye.
Bye.
לא רע בכלל.
תודה. Thank you.